Okay, so the topic of quantum physics will be dealing with a new idea of looking at EM radiation. Because in your AS, right, you used to consider EM radiation as waves, right now. Okay, so scientists later on, that means after Newton's era, people like de Broglie and Einstein, so they actually found out that you cannot explain all the phenomena in this world if you treat EM radiation to be just as waves. So one of these phenomena that you cannot explain if you treat EM radiation as waves is photoelectric emission. So what is actually photoelectric emission, right? So this guy Hertz, right, what he did was, when he applied a voltage across two electrodes, right, he noticed that you need a very high voltage before sparks start to jump lah. So why will the sparks jump out at a very high voltage? Is because if let's say this is positive and negative, so then the electrons will be pulled to the left and the nucleus will be pulled to the right, right? So when the force is large enough, then the electrons will be stripped off the atom and then they will start moving, and so then you see the sparks lah. But what he also realized that if you use ultraviolet radiation, that means if you shine ultraviolet radiation onto these plates here, what will happen is the spark started to jump at a way lower voltage, which means to say the ultraviolet was actually causing electrons to escape from the surface. Alright, so the idea is, of course, we got to shine on the left hand side, so better draw for you. So you shine on the negative side, alright, so then you will get the electrons coming out from the negative plate and then moving on to the positive plate, so then you will see the sparks lah. So this phenomena, that means they found out later on that if you want electrons to be emitted from the surface of the metal, you will need EM radiation of sufficiently high frequency. So the phenomena of photoelectric emission, this is the definition: emission of electrons from the surface of metal when it's exposed to EM radiation of sufficiently high frequency. Now you will notice that different metals require different minimum frequencies. For example, like zinc requires ultraviolet frequency and above. That means if you use any frequency less than ultraviolet, no electrons are emitted, no matter how long, no matter how intense the blue light or the red light, not a single electron comes out. Similarly, sodium needs blue light frequency and above, cesium needs red light frequency and above. So this minimum frequency to cause photoelectric emission is called the threshold frequency, alright, which is given in your notes as well as your definition. So the first thing that scientists couldn't understand was this thing: why is there a threshold frequency? Because you see, if you consider EM radiation as waves, then there shouldn't be threshold frequency, because the idea is, if let's say you had let me just change the color. If let's say you had this metal surface and inside got a lot of electrons, if you shine ultraviolet onto the surface, then the idea is, then the electrons which are inside here will keep absorbing the energy from the ultraviolet. When it gets enough energy, it will escape, right? So if you use a lower frequency, let's say you use blue light or you use red light, the waves will contain less energy, but wouldn't that mean that you just have to wait a bit longer? Sooner or later you will surely be able to accumulate enough energy to escape, right? But it doesn't happen. See, so that is the problem. If wave theory means, if you consider that as waves, then there shouldn't be a minimum frequency. Whatever frequency that you send in, you just continue to absorb, finally it comes out when you get enough energy. But it doesn't happen like that. And the second thing that was puzzling scientists was the instantaneous emission of electrons. That means if you shine, let's say, ultraviolet and above on zinc, the moment you shine ultraviolet, it straight comes out. It is as if they don't even have to accumulate the energy. They just come out straight away. So the first two observations that show you that EM radiation don't behave as waves is, number one, your instantaneous emission. Number two, the existence of threshold frequency. So that these two observations were puzzling scientists. So what they did next was they did another experiment. So the next experiment that they decided to do was to investigate what are the factors that affect photoelectric emission. So they actually considered two things. One is the intensity of the EM radiation. For example, if you're using blue light, a more intense means a brighter blue light lah. And the second thing they're testing is the frequency of EM radiation. So you don't use blue, then you use ultraviolet. You don't use ultraviolet, you use X-ray. So those are the frequencies of EM radiation. So they wanted to actually investigate what factor affects the number of electrons that are emitted. They call it the rate of emission. And number two, what affects the energy of the electrons when they are emitted. So the experiment is very straightforward. You have this tube here. C is actually your cathode because it's actually connected to your battery here, and D is your anode lah. So what will happen is, as you shine the ultraviolet onto zinc, for example, you will expect the electrons to be emitted, right? And they will travel over to the positive side because, of course, it's attracted to the positive terminal here lah. So the electrons which are emitted here will be attracted to the positives. So what will happen is, as the electrons travel, it will produce a current. Can you see that? So the voltage that you apply across the plates is measured using a voltmeter lah. So you plot a graph of current versus voltage. So logically speaking, the higher voltage you apply, the faster the electrons will move, right now, because it is more positive lah. Agree or not? So therefore, the first part is logical, it rises. So let's look at the first curve first. So it rises here from 0 volts, and then it rises. So then many people ask me, why at 0 volts, you still have a current? It's because at 0 volts, if let's say this was just a wire, so there's no voltage here, if you shine the EM radiation, the ultraviolet on zinc, the electrons still escape, right now? So when it escapes, this plate becomes positive because it lost an electron. The electrons travel over to this side, becomes negative. So then the electron will travel back to here, from negative back to positive, or still got current. You understand? It's just that when you increase the voltage here, then it travels faster. That's why you get a larger current. Okay, but then they realize that when you increase the voltage, it will actually become constant. The current actually becomes constant. So your current cannot increase anymore. So why? It's because the current is defined as what? Rate of flow of charge, remember? Which is number of electrons times the charge of electrons over time, right? So what will happen is, the rate of emission of the electrons, let's say you're emitting 10 electrons per second. But initially, we are using a low voltage here. What will happen is maybe only 5 or 6 electrons can reach per second. But when you increase the voltage, it moves faster. Now 8 or 9 electrons can reach per second, so your current increases. You increase the voltage more, then let's say 10 electrons reach per second. So that's your maximum current. Because if you try to increase the voltage further, you cannot have more than 10 electrons reaching this plate per second because you are only producing 10 electrons per second. So it is limited by the rate of emission of electrons. You cannot go higher than that. You understand? So that explains your maximum current. So if you get your maximum current, you can calculate the number of electrons emitted per second using back the same formula here. So if you know your maximum current, which is rate of flow of charge, which is number of electrons times charge of each electron. So your number of electrons per unit time is I over E. So you measure your maximum current, divide by the electron, the charge of electron, you get the rate of emission of electrons. Understand? So this is the first formula. So it's very, very useful, this first part. Then what they did was they increased the intensity. So they use a brighter ultraviolet, because ultraviolet is invisible, so you can't really see it. But let's say you use a brighter ultraviolet, just imagine. So they will get a higher current, which is logical. Because if you use a higher intensity ultraviolet, you expect more electrons to come out. Agree or not? So therefore, you get a higher current. Okay, now, so this part is quite logical. You keep increasing the intensity, more electrons emitted, so therefore your maximum current is higher. So now we know what factor affects the rate of emission of electrons, which is intensity of EM radiation, which is logical. But if you wanted to investigate the energy of the electrons, then what should we do? We must reverse the polarity. So what do you mean by reverse the polarity? So remember your C and your D here. Instead of connecting it to negative and positive like this, we switch polarity. So now we switch this to positive and negative. But we still shine the ultraviolet onto the cathode, which is actually now not a cathode because it's connected to positive, but let's call it C. So let's call it C. So the electrons will be emitted from the C, but instead of being attracted to D, now it will be repelled by D, because now this is negative and this is positive, this is negative. So therefore the electrons here, which is trying to reach this plate, will now be repelled right now. So instead of moving faster, it will start to move slower. So this negative voltage is indicated by this side, your negative voltage here. So as you increase the voltage here, more and more negative, it will start to slow down even more right now. So therefore your current starts to drop. Can you see? So you keep increasing this voltage until there's no more current being detected here. Because remember your ammeter is here. So the moment your ammeter shows you 0 reading, it means that now there's totally no current flowing. That means what? You have stopped the most energetic electrons. You see, when the electrons are emitted from this surface, right, they will have, different Ke one. Okay, why? Because some electrons are at the surface, so they need the least amount of work to escape from the attractive forces between the electrons and the nucleus. Because you see, when the electrons want to escape from the surface, it must overcome the attractive forces between the nucleus and the electron. Understand? So if they're deeper inside the metal, they have to do more work to escape. So they will come out with less Ke. The electrons at the surface will be the easiest to escape. So you have comes out with the highest Ke. So they come out with different Ke, which explains why when you increase the voltage, not all of them will stop straight away. The current will decrease, because the more energetic electrons can still reach, but the less energetic electrons will be stopped. So you keep increasing the voltage here until the current becomes 0. You see this current 0? The voltage here is called the stopping potential. So what you have done is you have managed to stop the most energetic electrons. And we can calculate its energy now, its Ke. Because the energy of the electrons is given in the topic of electric fields. When you try to stop it across, when it travels across a PD, the change in energy is QV right now. So you have your maximum Ke here, which is equals to QVS. That means this is the stopping potential. Because why? With this voltage, all the Ke changes to 0. Because you cannot reach the plate anymore. So you cannot reach the plate anymore means the electron comes out and then it stops here. So all the Ke here becomes 0 here. So the change in energy, which is Ke max, actually Ke max minus 0, is equals to QVS. You understand? So therefore, we get a second equation which tells us how to measure the maximum Ke of the electrons. So first formula tells you how to calculate the number of electrons emitted per second. Second formula gives you the maximum Ke of the electrons. But something very unique about this second observation, about this maximum Ke, you notice that if I use a higher intensity, you would expect, since you are supplying more energy, the electrons should come up with more energy, right now. But do you realize, even with higher intensity, your stopping potential is the same? All three graphs have the same stopping potential. So what does that tell you? It tells you that the maximum Ke of the electrons is independent of intensity of EM radiation, which is the third observation that puzzled scientists. Because if EM radiation are waves, and you supply more energy, so by right the electrons must come out with more energy, right? But it said no, it still comes out with the same maximum Ke. Why? So later on, scientists found out there's only one factor that affects the maximum Ke of the electrons, which is our next slide. So they realized that the only factor that affects the maximum energy of the photoelectrons is the frequency. So you're actually plotting versus frequency. So the higher the frequency of EM radiation, the higher your maximum Ke, but provided you start from the threshold. So at the threshold frequency, it will start to emit electrons. Below the threshold frequency, got nothing one. Understand or not? But above the threshold frequency, the higher your frequency, the higher your maximum Ke. So why? So that was the one puzzling scientist, because this is a fourth observation now. Because you see, if you supply more energy to the electrons by using higher intensity, no difference to the maximum Ke. But if you supply more energy to electrons by using higher frequency of EM radiation, you get higher Ke. So why it depends on frequency and not intensity? Because both we are supplying more energy, right? So therefore, these are your four observations that show that EM radiation do not behave as waves. Number one, the instantaneous emission of electrons. Number two, there's the existence of threshold frequency. The definition is here. And then you have why the maximum Ke is independent of intensity of EM radiation, and maximum Ke only increases with frequency of EM radiation. So this was one of the phenomena that challenged scientists' idea of EM radiation. All the while, they thought EM radiation were waves. But this phenomena of photoelectric emission shows you that EM radiation may not behave as waves. So who managed to explain photoelectric emission? Einstein. Okay? So how did Einstein manage to explain the phenomena of photoelectric emission? He actually borrowed an idea from Max Planck. So Max Planck was the first scientist of that era who suggested that EM radiation are not waves. He suggested that EM radiation, they are particles. So what kind of particles did he say that EM radiation is or are? He said that they are actually packets of energy called photons. So instead of imagining the EM radiation coming to you as waves, you can actually consider them as packets of energy. And according to Max Planck, each packet of energy, which is called a photon, its energy is given by this equation. E equals to hf, which is h is Planck's constant, f is the frequency of EM radiation, so the E gives you the energy of each photon. If you want to convert f to wavelength also can, remember the formula V equals to f lambda. So your f equals to V over lambda. So your f here, you can change to C over lambda. Why C? Because all EM radiation travel with the same speed, which is speed of light and vacuum. So C is the speed of light and vacuum. So you can either use E equals hf or E equals hc over lambda. That is your third equation, which is the energy of each photon. Then what Max Planck did was, he left it there. Then Einstein saw this idea, and he decided to use this idea to explain photoelectric emission. So this is how Einstein explained it. He says that, number one, he said the assumption is this. Every photon can only interact with one electron at a single time. So let's say this is your photon. It can only interact with one electron at any single time. Okay? You cannot have multiple photons absorbed by the electron. At one time, only one photon is absorbed by the electron. If the energy contained by the photon is sufficient for the electrons to escape, it will escape. But if the energy contained by the photon is not enough for the electron to escape, it will not escape. The energy will be used up before a second photon can be absorbed. So you cannot say, oh, first photon not enough, so absorb a second photon, not enough, absorb the one, finally come out. No. Because Einstein says only one photon interact with one electron. If enough for it to come out, it comes out. Not enough to come out, the energy is used up before a second photon is absorbed. Because why? It happens so fast. Before the second photon can be absorbed, energy is used up. How? Maybe either it just moves faster a bit, or there's another idea which says that the photon won't even be absorbed because it doesn't match, so it refuses to absorb. Okay, so that's the idea behind the photoelectric emission. But if it's enough energy to absorb, it will come out. So that explains why there's a instantaneous emission of electrons. There's no accumulation of energy. Right? One photon absorbed by electron, enough come out straight away. No need to wait. So you explain instantaneous emission. And number two, you also manage to explain threshold frequency, because the energy of each photon, remember, depends on the frequency. So if you have a minimum energy here, that means you need a minimum frequency here. So what will happen is, if you supply a lower frequency EM radiation, let's say you supply red light, so the frequency is lower, the energy of each photon is lower. So what happens is, either it absorbs but it doesn't do anything, or it just passes through, it refuses to absorb. So even if you send more, it doesn't matter. So you increase the intensity of EM radiation of red light, for example, for zinc, nothing happens. No matter how long you wait, not a single electron will come out. That's what happened. Because if you use zinc and you use lower than ultraviolet, no matter how intense the let's say the red light, no matter how long you shine, not a single electron comes out. Because the energy contained is not enough. So you cannot keep on accumulating. It's only one electron and one photon. If you have enough, it comes out. Not enough, nothing happens. That's it. Third observation, right? Remember we said the maximum KE is independent of intensity of EM radiation. Now, let's say you use ultraviolet so it can come out, and we increase the intensity of ultraviolet. What you are basically doing, you are increasing the number of photons. You are not increasing the energy of each photon. Why? I'll show you the formula. So since intensity is energy per unit time per unit area, right? Remember in your AS, intensity of EM radiation, which is power per unit area, remember? So the energy is actually number of photons times the energy of each photon. That's what you're saying. Because the energy of the EM radiation, alright, which is this one, is given by the photons. So you got number of photons times the energy of each photon gives you the total energy of the EM radiation. So if you increase the intensity here, since the energy of each photon remains the same, because you did not touch the frequency, the energy of each photon depends only on the frequency. You're using the same frequency, but you increase the intensity, the energy of each photon remains the same, but intensity higher means the number of photons per unit time is higher. So you're actually supplying more photons. When you supply more photons, what happens is more electrons will come out. That's why, remember, when you have higher intensity, your current is higher. Correct or not? But why doesn't your electron come out with more energy? Because each photon still contains the same amount of energy. So every electron that absorbs will still have the same maximum KE. Right? Can you see that? And finally, the fourth observation, the maximum KE is will increase with frequency of EM radiation, because once you increase the frequency of EM radiation, the energy of each photon increases. So therefore, when the electrons absorb it, of course it has more energy to come out, so the maximum KE increases. Alright, so this is how Einstein managed to explain photoelectric emission. So therefore, this this is intensity. This formula for intensity is your third equation you got to remember. So don't be confused. Sometimes the I represents intensity, sometimes the I represents current. So you better be careful what the I represents. Okay, if for the photon, your I it represents intensity. But if for electron, the I represents current. Okay, so be careful about that. Okay, so the next diagram tells you why the electrons come up with different KE. All right, let's look at what happens here. If we look at the first electron here, okay, let's look at the first electron here. It is right at the surface, right, of the metal. So this is a photon. Once the electron absorbs a photon, because it's at the surface, it requires the least amount of work to escape, so it comes out with the highest KE. Now, electron number 2 is so deep inside the metal such that when it absorbs the photon, by the time it does work to try to escape, it has no more KE, so it gets sucked back in. The third electron is slightly inside compared to number 1, so it comes out with slightly less Ke. Electron number 4 is the sad case. It was at the surface, but it so happened to be traveling inwards when the time when it received the photon, so it went deeper. So it never come out. So therefore, you will notice that not necessarily every photon that has sufficient energy will cause one electron to come out. It also depends on where the electron is at and where and which direction the electrons are moving. So probably the ratio is about 1 million to 1. If you send in 1 million photons, for every 1 million photons, you probably only get one electron that comes out. Why? Because the electrons have to be at the right place at the right time, moving in the right direction. Then only it comes out. It's like you striking a lottery. Okay? But because you're sending in so many photons, of course you have sufficient electrons coming out lah. You understand? You still have sufficient electrons coming out to detect. But one thing you must realize, not every photon can cause an electron to come out, even though it has sufficient energy. Okay? That's what I'm trying to say lah. Right, so the next thing is Einstein came out with the equation for the photoelectric emission. They call it Einstein's photoelectric equation. So let's talk about his initial idea first. So his initial idea is conservation of energy. He says the energy of each photon will be absorbed by the electron, and that becomes the work done to remove the electron from the surface of the metal, and any balance becomes the Ke. Agree or not? Agree? An electron absorbs the photon, it does work to come out from the metal, any balance becomes a Ke. Now, but you must understand, because all the electrons have different Ke, because they are all different parts of the metal, so Einstein realized that he can find out one case accurately, which are the electrons at the surface of the metal. You know why? Because the electrons on the surface of the metal will have the highest Ke, right now. And remember, highest Ke you can calculate from the first equation, from the first slide, your Ke max equals to QVS, remember? Remember the QVS we did earlier on? So we actually can find the maximum Ke. So he modified the equation, this general equation, for these particular electrons at the surface of the metal. So he says, therefore, the energy of the incoming photon, which is a HF or Hc over lambda, is equals to the minimum work done to remove an electron from the surface of the metal. So that is called your work function energy. So this symbol here, work function, represents the minimum work done to remove an electron from the surface of a metal. So that is the definition of work function energy. So therefore, these electrons will have the highest Ke. So this is Einstein's photoelectric equation that you must memorize. Do you understand? And if you want to find out the formula for this work function energy, so let's talk about this. If you supply threshold frequency, there's a minimum frequency, then the electrons can come out but got no Ke. You understand? That's the minimum. So what will happen is your HF naught, which is your H times your threshold frequency, will give you your work function but got no Ke. So you get work function is HF naught. And you can modify a little bit more in terms of wavelength. Since V equals to F over lambda, so your lambda is V over F, right? Not? When you use the minimum frequency, you will end up with what? Maximum wavelength. Agree not? Because it's inversely proportional. So you will get work function is also equals to Hc over lambda max. Also can. So there are two formulas for work function again. Okay. Alright, so this is Einstein's photoelectric equation. This one. Energy of photon equals to work function energy. So what's work function energy? Minimum work done to remove an electron from the surface of a metal. Then plus maximum K. Right, so the graphs. Now, the first graph that we learned earlier on was in the first slide, which was like this, right? Current versus voltage, right? So that one we are done. So we're going to look at the second graph here, which is we are plotting actually Ke max. There's a Ke max versus frequency. So how do we get this graph? Very simple. If you take Einstein's photoelectric equation and rearrange the equation to make Ke max as subject, because this is my y-axis. I make Ke max as my subject, I'll get Hf minus work function, right? So since you're plotting Ke max versus F, so the Ke max is your y-axis, your frequency is the x-axis, what does the gradient give you? Threshold, Planck constant. And what does your y-intercept give you? Work function energy. Because you compare, the y-intercept give you negative of your work function. So therefore, you'll get this graph. Actually, starting from here, this one is you just extrapolate yourself. The graph actually starts from here. Okay? So you extrapolate yourself to get your work function. Alright? So this is the graph that you need to know. Okay, so now let's summarize the entire part, because it's so confusing, so many equations, right? Okay, so let me summarize for you. For photons, the first formula you need to know is the energy of each photon, which is E equals Hf or E equals h lambda. So if they ask you to find energy of photon, you just have to use this. Second formula for photons is intensity. If they give you the intensity of EM radiation, you can use this formula, which is energy per unit time per unit area. So the energy, total energy of the EM radiation is also number of photons times energy of each photon. So therefore, rearranging your number of photons per unit time is this formula. So you want to find number of photons, you use this. Third one, if they don't give you intensity, they give you power, so it's easier. So power is just energy per unit time. Always change the energy to number of photons times the energy of each photon. So number of photons per unit time is P over E also can. So you realize all this is about photons. For electrons, if they ask you, the first equation is actually Einstein's photoelectric equation. And the second equation is the formula for this work function. The third formula is for current. So this I here is current, this I here is intensity, don't confuse. If they ask you to find number of electrons per unit time or number of electrons, you can use current here. So current is rate of flow of charge. Total charge is number of electrons times the charge of each electron. And the final equation is your maximum Ke is QVS. So there are two graphs that you also need to know. The first graph is current versus voltage. So you'll be like this and like this. So this is your stopping potential. The second graph is your Ke max versus frequency is like this. So if you extrapolate, you will get your negative of your work function, and the gradient will give you your what? Planck constant. Two graphs. Okay? So this summarizes the entire part of photoelectric emission. So this Einstein's explanation of the photoelectric emission won him his only Nobel Prize. All right, because the other ideas that he had, for example, the more famous equations like E equals mc squared. You know why he didn't win a Nobel Prize? Because that equation is actually for what? Right? For nuclear bomb. Okay. He actually designed it because at the time, remember, Germany was actually like exterminating the Jews, because he's a Jew, right? So he went to US and helped them design the atom bomb to fight against the Germans. So Nobel Prize is for peace, not for killing people. So even though it's a very good discovery, but he doesn't qualify for Nobel Peace Prize. Second one is another famous idea was, remember, the theory of relativity. Alright, so theory of relativity was too radical at that time, such that other scientists didn't believe him. So because of that, they didn't give him a Nobel Prize. Later on, when other scientists proved that this was correct, then they actually realized that, okay, he's correct, but they didn't give him anymore.
He died.
I don't know whether he died or not, but I think they by the time they proved his theory correct, I think he was still alive. But anyway, too bad so he didn't win the Nobel Prize for even the other things So we only won for photoelectric emission. The sad case is it wasn't his original idea. He even borrowed the idea from Max Planck, right? So conclusion is, if you do everything yourself, you may not get anything. Better you just steal people's idea, you may get something from it.